Okay, welcome back everyone. In this video we're going to be discussing conservation of momentum. We're going to continue practicing the concept, and this is an example of how you apply conservation of momentum to what we call an elastic collision. And we're going to stick with one-dimensional to keep things a little simple. So previously you learned that conservation of momentum means that the total momentum before a collision is equal to the total momentum after a collision. Or in other words, using Newton's second law, F equals change in momentum over change in time, where F is 0. Okay, so that's just a reminder, and that gives us a change in momentum, which is equal to 0. Okay, so how do you use conservation of momentum with elastic collisions? Typically, you're given a situation where you have two unknowns. For example, this is number 84 on page 212. And the problem states that at a county fair, two children ram each other head-on while riding on the bumper car attraction. Jill and her car, traveling left at 3.50 meters per second, have a total mass of 325 kilograms. Jack and his car, traveling to the right at 2.00 meters per second, have a total mass of 290 kilograms. So we can label this the initial or before diagram. Now what we need to find is, assuming the collision to be elastic, determine their velocities after the collision. So we can call this object 1 and object 2. What we are looking for is V1 final and V2 final. We don't have any clue which way they're going. Now we can guess. We can make a guess that since Jill is more massive and traveling faster, that the system overall is going to have momentum going to the left, and we'll see that in a moment. And we could guess that Jill's going that way, but we don't really know, so we're just going to leave it. But this is the final picture, so we don't know which way they're going. Now when we solve elastic collisions, there are two main equations that we need to solve simultaneously. First, we're going to have conservation of momentum. So that means that the initial momentum total is equal to the final momentum total. And because it is an elastic collision, what that means is that no energy is lost in the collision. Now in real life this almost never happens, but this is make-believe learn physics land, and what this says is that basically the change in kinetic energy is going to be 0, just like this equation says the change in momentum is 0. And so what that means is that the kinetic energy initial total will be equal to the kinetic energy final total. So now all we have to do is write equations for these. Okay, so I'm going to set up these equations, and we'll go from there. We'll see what happens. So we'll start with momentum. Okay, and just to be fun, we'll say that anything going to the right is positive. Okay, so that means that Jack has got momentum of 290 times 2, and that's positive. And we're going to add to that Jill's momentum of 325 times negative 3.5. And I'm leaving all of the units out, but this is the initial momentum total, the total momentum of the system before the collision. Now because of conservation of momentum, we know that that's going to be equal to the final momentum total of the system. Okay, and we still know that Jack's mass is 290 and Jill's is going to be 325. So we can write that Jack's momentum will be 290 times V1 final, and we can also write that Jill's will be 325 times V2 final. Notice this positive sign here. I'm not trying to make any guesses as to which way the two objects are moving. The math is going to tell me whether V1 final and V2 final are positive or negative. Okay, so far so good. And actually, if you crunch the numbers on the left side, you're going to get negative 557.5, and on the right you'll get 290 V1 final plus 325 V2 final. And like we said a moment ago, it looks like the initial momentum of the system is negative. And turns out that the final momentum of the system will be negative 2. Okay, now let's set up the kinetic energy. And for this, we know that the kinetic energy initial total, in other words before the collision, is going to be 1/2 Jack's mass times Jack's speed squared plus 1/2 times Jill's mass times her speed squared. Notice that it doesn't matter if I put in a negative for her velocity. It's going to get squared anyways. Okay, and that's going to be equal to the final kinetic energy of the system. So I'm just going to write it down here because I'm running out of space. It's going to be 1/2 times Jack's mass times his final velocity squared, which is an unknown, plus 1/2 times Jill's mass times her final velocity squared, which is an unknown. So we have two equations and two unknowns, but first let me simplify this second equation a bit. And I did the calculations prior to the video, so it's 2570.625 equals 145 V1 final squared plus 162.5 V2 final squared. Okay, now I hope you're not scared by a little bit of algebra, but here are the two equations that we have to solve simultaneously. Okay, so we're going to solve these for V1 final and V2 final. Okay, now just to save a little bit of time, I'm going to kind of do some magic here. Okay, so I'm going to pause the video and I'm going to write out the solution. Okay, you ready? I'm going to pause it. Oh, and you can see that there's some magic algebra skills going on here. And let's just pause it one more time, and there we go. There are our final answers. Now, I can assure you that I spent about 15 minutes actually solving this system, and it's kind of a pain. So when you get a problem like this, the book actually lists a couple of equations. So these are equations 6.14 and 6.15. They're in the back of the chapter and you can find them. And these are perfectly valid for solving elastic one-dimensional collision problems. Okay, so if you want to use these, that's totally fine. But you need to make sure you understand the basic concept, where these equations come from. You need to understand that these equations originate from total momentum is equal to 0, so P initial equals P final, and the change in kinetic energy is 0, so kinetic energy initial equals kinetic energy final. And that's where these equations are derived from. So in other words, you do need to understand where these two equations 1 and 2 come from. You need to know how to find them, because I can guarantee that on your test/quiz you're going to get an elastic collision, even though it may not be quite as nasty numbers. Now a little bit later on, I'm going to show you a really quick and easy way to skip all the algebra skills and get pretty much directly to the answer. But we'll save that for a later one.